Okay, this is the takeaway video for Chapter 11, Intermolecular Forces, also discussing vapor pressure, boiling point, phase diagrams, things like that. Okay, so vapor pressure is defined as the vapor, let me back up, the pressure exerted by a vapor above a liquid. Vapor pressure happens when we have a closed container, okay? So a beaker with a lid on it, a water bottle, something like that. And what happens is you have your substance, let's say it's water, and eventually some of those molecules are able to escape the liquid phase and they turn into a gas, they vaporize, okay? And so initially, when you cap your container, the vapor pressure starts to increase, okay? Because think about it, initially there was no vapor pressure, and so as those molecules vaporize, they create that pressure above the liquid. So the vapor pressure starts to increase. But eventually, what happens is we have a situation where we have molecules evaporating just as quickly as those molecules are condensing. And so eventually, the vapor pressure stays constant, and we enter a state called dynamic equilibrium, and that's where the rate of, of evaporation equals the rate of condensation, and we refer to this as there being no net change. This is why you could never have a capped water bottle that would evaporate completely, because as the evaporation is occurring, you also have condensation occurring. Okay, so keep that in mind. We encountered a vocabulary word that is the word volatile, and the word volatile means like the ease in which liquids evaporate. A lot of people think volatile means reactive. That's not really what it means. It just means how easily a liquid evaporates. And so volatile liquids have pretty weak intermolecular forces. Think about it, because to evaporate, you have to break those intermolecular forces. So if you have a substance that readily evaporates, those forces are being broken pretty easily, and that means that they're weaker. So for example, water is not considered volatile because it has such strong intermolecular forces. It takes a lot of energy to make water evaporate, but like rubbing alcohol is very volatile. It evaporates very quickly because it has weak intermolecular forces. A second discussion in vapor pressure is the boiling point, and the boiling point of a liquid is when the vapor pressure equals the atmospheric pressure. And so what we learn right here is that boiling point actually depends on atmospheric pressure. And so because of that, we have to define something called a normal boiling point, which is the boiling point at 1 ATM, okay, or like sea level. So that's why if we have a city like Denver, okay, Denver's not called the Mile High City for nothing. It's very high in elevation. So if we have a pressure of 1 ATM at sea level in Denver, that pressure is less than 1 ATM, because as you increase your elevation, the pressure decreases. That's why it's hard to breathe in Denver. There's less oxygen. And so actually, because the pressure is lower, the boiling point of like water, for example, is actually lower. Water boils at about 95 degrees Celsius in Denver, and at 1 ATM, of course, it boils at 100. So it's not a huge difference, but big takeaway is that boiling point does depend on atmospheric pressure, okay? Big deal. So changing the pressure, we can actually change the boiling point of a substance. So that's kind of interesting. Okay, we also learned about phase diagrams, which are basically pressure and temperature graphs of a substance. Okay, we learned that we can label the solid, the liquid, the gas phase for whoever this is. We also learned that as we cross this line this way, that would be the process of fusion or melting, solidification, evaporation, condensation, sublimation, deposition, okay? And there's two important points on this graph. This is the triple point. The triple point is where you have, it's the pressure and the temperature where all three phases, coexist in an equilibrium situation. And this is the critical point. We talk about beyond here, there's really no distinction between the liquid and the gas. And we can look at a phase diagram to answer the question of, like, will this substance sublime at room temperature and pressure? And that's where we compared, like, H2Os and CO2s. And we were able to come to the understanding of, why water does not, or I should say why water melts at room temperature and pressure, and why CO2 sublimes. And it's because their phase diagram is so different. So every phase diagram is going to be different for each substance. We can also find things on the phase diagram like the normal boiling point and melting point. So for example, I've just made this up, but normal, of course, 1 atm. So this right here, right, would be your melting point. And this right here would be your normal boiling point for those, for that substance. Okay, so a lot of information contained in a, a lot of information contained in a phase diagram. Okay, so then the bigger discussion is intermolecular forces. But before we really talk about intermolecular, we have to also talk about intra. So intra is the force that holds atoms together, right? A for intra. And so there are two types, ionic and covalent. So if we talk about water, which tends to be our favorite thing to talk about, this is an intramolecular force, and that's the covalent bond, okay? Very hard to break in intra. To break an intramolecular force, that's a chemical reaction, okay? But different from that is inter, which holds molecules together. We know that there are several types of intermolecular forces, and basically we're looking at what is it that attracts this and this together, okay? So what is it that holds one H2O to another H2O? And those are called intermolecular forces, okay? They take much less energy to break, and when you break inter, that's when you have boiling, okay, or vaporization. All right, there are technically 4 types of intermolecular forces, and these are ranked by strength. So you can just put a little whoop up the side of your notes here. So ion dipole involves an ionic substance dissolved in a polar liquid. So most often we talk about, this is my favorite example, but we talk about NaCl in water. So if you think about NaCl, it ionizes. We have water, which is a polar substance, partial negative and partial positive. So here your Na is going to scoot over here, and your Cl is going to, what just happened? That's a positive. Okay, there it is. And your Cl is going to scoot close to your partial positive, and that's a ion dipole force. Okay, it's pretty strong because it's a full-blown ionic charge, and then with a partial charge. Only though occurs in ionic substances in water. So it's the one we see the least of, but it is technically an intermolecular force. The second strongest is hydrogen bonding, and this is a H on an N, O, or an F that's attracted to the lone pair on another N, O, or F. So common misconception, a lot of students think hydrogen bonding just has to have a hydrogen, right? Not true. It has to be a hydrogen on an N, O, or an F. So like HF, for example, there's a hydrogen bond that exists between the H and the F. And remember, it's designated with the 3 dots, and it's kind of silly, but that's how they designate a hydrogen bond. Dipole occurs in polar molecules, and it's the partial charge attraction. So keep this simple, maybe like HCl, right? That's a polar bond. And so if I brought another one in here, they would align themselves like this. And that is the intermolecular force of dipole-dipole. It occurs only in polar molecules. And your weakest type of intermolecular force is dispersion. It occurs in all molecules, right? But it is an instantaneous dipole caused by the motion of electrons. And that motion of electrons is called polarizability, and that's the ease in which those electrons can be distorted or moved around to create those instantaneous dipoles. And so, we often have a comparison of two diatomics, which only have dispersion forces, and we're asked which one has stronger forces. Okay, and so in this case, it's Br2 because, Br2 has a larger molar mass, which makes it more polarizable. And it's the fact that it's more polarizable that it has stronger intermolecular forces. Okay, so this is an interesting topic, and they'll try to get you on the exam. The reason that Br2 has stronger intermolecular forces is because it's more polarizable. And because it's more polarizable, those instantaneous dipoles can be created more easily. However, it's more polarizable because it has a bigger molar mass, okay? More electrons. So that's pretty confusing, but it is the increase in polarizability that affects the strength of your intermolecular forces. Again, quickly, we know that lots of molecules can exhibit more than one type of intermolecular force. So some questions will say list all of them, and some might say list the strongest type. So be mindful of what the question is asking you. And the last thing was looking at these heating curves and talking about energy. And so we learned that these heating curves show us two important temperatures, which are the melting point and the boiling point for whatever substance we're looking at. We know if this is water, this is 0, and this is 100, but that's not that's not true if this is not water. So in this case, we have a solid, we have a liquid, and we have a gas, and our plateaus are the phase changes, okay, that are occurring. So, and we know from class that we have labeled these sections as section 1, 2, 3, 4, and 5 to talk about them. During a phase change, the temperature stays the same. Big piece of information. That's because all the energy being put into that is used to change the state of matter and not to raise the temperature. And so how do we calculate the energy associated with these sections? Well, in sections 1, 3, and 5, where we're either raising or lowering the temperature of something, we can do that by using MC delta T to solve for that amount of energy or heat. And in sections 2 and 4, though, we have to use what I refer to as delta H and a little bit of dimensional analysis. Because it's a phase change, I cannot use MC delta T. And so this is where we would talk about, for water, that there's a delta H of fusion and there's a delta H of vaporization. And we know how much energy it takes to melt and to vaporize a mole of water. But secretly, right, we made a big deal about this, they also are giving us 2 more, which are the opposites, right? Because the opposite process is just going to be exothermic. And so that brings me to my very last point, which is if we're coming down this chart, these are exothermic processes, and every energy amount we calculate is going to be negative to show that that energy is being released. And if we're moving up the chart, right, those processes are endothermic, and every energy we calculate is going to be positive to show that that energy is going in to the thing that we're discussing. Okay, so that is that's a little bit of endo and exo contained in these heating curves.